Welcome to the fourth video on the octave range from impedance. In this video, we will be exploring the applications of the octave for measuring and displaying pulsed power. Pulsed RF sources are being used more frequently in plasma reactors. The octave sensor is capable of providing voltage and current data with time resolutions down to 1 microsecond. Time resolved is used to capture RF parameters during an RF pulse period. Time resolved mode develops a profile by capturing the shape of a pulse frequency. To demonstrate this, we hooked up an octave unit between a signal generator with an RF amplifier and a 50 ohm load. A pulsing RF generator may also be used. We also set up an oscilloscope, probing the line between the 50 ohm load and the octave unit. We connected the octave to our laptop via a USB cable. For best accuracy, the octave should be allowed a 10-minute warm-up period. We then open the octave dedicated software by clicking the icon on the desktop, or you can go to the program in the program menu, or you can just use the search tool on Windows 8 or later and type octave. You can see that for this demonstration, we are using an octave suite, though the octave poly and the industrial octave will both be able to measure pulsed RF. Under sensor configuration, we set the number of harmonics to 8 in the 13.56 MHz range, and left the signal lock at voltage. The start and end time of a scan can be user-defined if only a certain section of a scan is needed to be examined. The time step allows a definition of the size of the steps between readings. This is the time resolution of the scan. The averages function measures the amount of periods recorded at each point. Selecting a large amount of averages will help to reduce noise levels in a scan. However, this will also increase the amount of time taken to complete a scan. Lower averaging values will increase scan speed, but will also increase signal noise levels. Internal trigger allows the octave to synchronize to the rising edge of the pulse profile using a voltage level threshold. The octave must be told the pulse frequency and the voltage level. When the level field is left empty, the software uses half the peak voltage at the time the scan is started as the trigger level. Internal trigger should only be used for single frequency systems. For multiple source frequencies, an external trigger source is recommended. We input 10 kHz for pulse frequency. AutoSet takes a fill period of 10 kHz signal and adjusts to pulse frequency, auto-filling in the fields above. You can modify these. The automatic settings will configure the scan to start from the trigger time to the end of the pulse. Under parameter view, we check the box for power, as this is the parameter we want displayed in the graph area. Here we have selected power, but any parameter can be used. Hit Start Scan. The profile of the pulse will be displayed in the graph area. The automatic settings have configured this scan to start from the trigger time to the end of the pulse. We will now rescan with pre-trigger data. Because the trigger occurs during the rising edge, we don't get a clear plot showing the rising edge. We can reconfigure the scan to start before the rising edge by entering a negative time value into the start box. In this case, we set it to -10 microseconds. This time, we're going to rescan with increased resolution. The AutoSet feature configures the time resolution to get 50 points for the pulse period. For the next scan, the time resolution is increased to 1 microsecond. Also, since in this case we are only interested in the on time, we adjusted the end time to 40 microseconds. The pulse timing has been adjusted to 10% duty cycle, as you can see in the oscilloscope. Here, the pulse time has been adjusted to 20%, as you can see in the oscilloscope. and here, the pulse timing has been adjusted to 75%, as shown in the scope. As the pulse on has passed our scan end time, we reset our scan end time to 100 microseconds and the scan is retaken. Each point in the pulse scan contains a full set of voltage, current and harmonic data. This allows us to see the waveform shape and how it evolves during the pulse. Here the scan is repeated using a sinusoidal RF source.